Okay, so the first speaker this morning is Richard Sharp from Warwick, and about a non-symmetric Kesten criterion for random walks on groups.
Okay, thank you. Well, so thanks very much for the organisers for inviting me to speak here. What I'm going to talk about is joint work with Rhiannon Dougall. So originally, Rhiannon was going to give a talk here as well that was going to be kind of linked, but she's not able to come. So I'm going to try and include something of what she would have said as well, which might make things a bit pasty or whatever, but anyway. And apologies, I'm going to try and keep this accessible, so apologies if I'm telling people things they already know really well. Right, so I want to talk initially about random walks on groups. So G is going to be a countable group with identity element E. And we're going to have a probability measure giving the random walk. So mu is from G to R plus. Is a probability measure. So, of course, you start somewhere and then you move by multiplying. I multiply on the right by some element with probabilities given by this. And we're always going to assume that this mu is what I call non-degenerate. And this means that the support, so the support is just the set of elements that have positive measure. So it's G in G such that mu of G is greater than 0. This generates G as a semigroup. Okay, so even if I don't say this explicitly, I always assume this. Okay, and well, I've forgotten how heavy these ESI boards are. Probably balanced though. Anyway, so I'm going to be talking a lot about this thing. The nth convolution may be evaluated at the identity or any other group element, particularly at the identity. So this is the probability of going from E to E in n steps. If I put in another group element, I don't know what's visible. Let's try this one. This would be the probability of going from the identity to this group element in n steps. And associated to this, we might like to understand this, but one basic thing might be to understand its growth rate at an exponential level. So we have something that's called the spectral radius, and I won't exactly say why it's a spectral radius. If you don't know, it doesn't really matter. So let me call this lambda of G and mu, and so this is going to be, by definition, the lim sup as n goes to infinity of this convolution to the 1 over n. And in fact, if you go along even n, it's a limit, but this will do. Okay, and then there's a famous theorem of Kesten from the end of the 50s. That, so let's do something about this. So this number is always less than or equal to 1. if you, I'm just thinking of some simple examples, if you had simple random walk on the integers or a higher dimension integer lattice, it would be 1, you can easily work out. If it was on the free group, non-abelian free group, it's less than 1. So when is it 1 and when is it smaller than 1? And Kesten, in the case where the measure is symmetric, tells us exactly. So maybe I should actually just write this as a separate definition. So mu is symmetric if mu of G inverse is equal to mu of G always. Okay, and so Kesten's theorem is mu symmetric. Maybe if mu symmetric, then lambda of G mu is equal to 1 if and only if G is amenable, okay, and less than 1 otherwise. Okay, so I guess this is one of the early results in the theory of random walks on general groups, not just, say, integer lattices. And subsequently, there were lots of analogous so-called amenability dichotomies in, in group theory. There's the Grigorchuk-Cohen Crogrove criterion that I won't talk about. Also in geometry and dynamics. So one result, could say, is due to Brooks from the 80s. So and this is about the spectrum of the Laplacian on manifolds and their covers. So we're going to have now here M is going to be a Riemannian manifold. I guess you want complete, maybe. And this is going to be the Laplacian operator, sign to be positive. And then we talk about quantity, so I'm reusing lambda, but let's call it lambda 0 of M is the infimum of the spectrum of this operator. Okay. So if M is compact, then this is 0, but it might be positive. Okay, and then Brooks is looking at the following situation. So you've got a regular cover. Let's say M tilde sitting over M with covering group G. And so you have the Laplacians for each of these two manifolds. And the lambda 0 for the cover is greater than or equal to get the inequalities right, is greater than or equal to what you have down here. So lambda 0 So when do you have equality? And you have equality essentially when this G is amenable. I mean, it gets a bit more technical than that. So, theorem of Brooks from 1985. So, if M's compact, Or, so if M isn't compact, Brooks gives a rather technical criterion I don't want to tell you, but a particular case of this would be, so or, M is a hyperbolic manifold, so it's a quotient of, say, D plus one-dimensional hyperbolic space by some group of isometries. This gamma is convex co-compact, and the lambda 0 for n is less than d squared over 4. So this is just a special case. It's a much more general non-compact condition. And the result is not specifically, though I'll talk about things in negative curvature, it's not specifically related to negative curvature. Okay, so if you have all of these things, then you have equality if and only if the covering group is amenable. Okay, so I think that's a very nice or geometric analog. And if you're in this second case of thinking about hyperbolic spaces, you can reinterpret this in terms of critical exponents. Okay, so if we just think about this situation, there's a number for each of the, well, for the group gamma, there's a number delta of gamma called the critical exponent. And so you can define this as by thinking about this series, for example, sum over gamma in gamma, e to the minus s, s is a complex variable, distance in hyperbolic space between some point O and OG. So this thing is going to converge if the real part of S is large enough, and in fact it's going to converge for real part of S greater than delta of gamma, and it's going to diverge the real part of S less than delta of gamma. Okay, so it's the abscissa of convergence of this series. That's how delta is defined. And so there's a relationship between these two quantities. And so a corollary is that if you have gamma as, well, above, I feel above means here, it was above in my notes, above, and you have a normal subgroup to give you a regular covering, then the critical exponent for the normal subgroup is less than or equal to the critical exponent for the group. Then you have equality of these exponents if and only if, so now the G is the quotient, gamma over gamma prime is amenable. So then this had various generalizations in the context of hyperbolic space and more generally. Which I won't go through in detail. But the results of Rob Lan, there's some results of mine, and Sattelbauer, or well, maybe I should say, the Roblan result tells you that amenability implies equality in the generality of cat-1 spaces. So it's really a lot more general. Well, actually, maybe I should write that down. And Sattelbauer's work, which I think is, rather than the results he actually gets in the context of hyperbolic space, is very important and introduce some new ideas using transfer operators, which, well, we've got to exploit in what's coming next. So I know, in one direction it's actually done level of cat-1 now, but in thinking about the other direction, knowing that you've got equality of the exponents, possibly implying amenability, you might ask what happens when you have variable curvature instead of constant curvature. And so that was done by myself and Dougall in 2016. So let me just say for variable curvature, variable negative curvature. And still in the setting of what you might call convex co-compact. So I didn't really say what that meant, but just think of not having cusps. Basically, you can have some infinite volume funnels, but you don't have cusps. And then further generalizations by Coulomb, Albo, and Sambucetti. Which does cat-1, and also groups acting on their Cayley graph, generalizing the Gorchuk-Cohen co-growth idea. And then the most general result is Coulomb, Dougall, Shapira, and Tapi. And I've been giving years by years of publication. This is to appear, but it was, I think, 2020 on arXiv, and it's to appear in the AMS memoirs. Okay, so all these results. So this is in the context of assuming the base is what's called strictly positive for current. So it's really very general. Right, well, so you can think about these results also geometrically in terms of, dynamically, in terms of the geodesic flow. Okay, so let's call it I sub t from the unit tangent bundle M2 itself. And then the critical exponent corresponds to the topological entropy. So let me call that H phi. And if you're starting with a base where you've got your M is some variable negative curvature, convex co-compact thing, this one way of characterizing this is growth rate of periodic orbits. So it's the limit, let's say, t goes to infinity, 1 over t log number of, let's say, gamma, a periodic orbit for phi with L of gamma least period less than or equal to t. And then, so suppose you've got, as before, a regular cover. What quantity would you want to define there? Well, you might want to try and define the same thing and call it, so think about the lifted flow, and think about this and call it the limb. Well, you don't know the limit exists, so let's say it's a limb sup. 1 over t log number of gamma, let's say gamma tilde, periodic orbit for pi tilde, such that periods at most t. But there's a problem with that definition, because if you've got an infinite cover and you take a periodic orbit, then you can just move it around by the covering group and get infinitely many with the same length. So this number would just be infinite. So what you need to do is say something like you take K contained in T1 of M tilde that's, say, open and relatively compact closure, and you impose the extra condition that you intersect with that. Okay, so, and then obviously the result becomes that this number is, so always this number is less than or equal to this number, and you have equality exactly when the cover is amenable. I'm sorry?
When you define edge of phi tilde, so you said you think it's K.
Yeah, it's independent of K.
Well, it is independent.
When you take the exponential growth rate. If you just took the asymptotic, it would depend on K. But yeah, it comes out in the wash, as it were. Okay, so so the geodesic flow, let's do some cleaning. The geodesic flow over a negatively curved manifold, well, let's say a compact one, is an example of an Anosov flow, transitive Anosov flow. And so you might ask, what happens in that case? Okay, so now imagine we've got pi t from, so I'm going to reuse M just to mean the phase space now. So previously I was thinking about the unit tangent bundle of a manifold M. Now that space in which the flow is just being called M. So this is transitive Anosov. Okay. So you might ask, you can have the same definitions of H for this flow and H for some, taking some regular cover and lifting the flow, and ask the same question, when do you have equality? But the result that we had in the case of geodesic flows is no longer true in general, because you can even find you can find the examples of these flows with Z covers where you get a drop in this growth rate. Okay, an example, let's say previous theorems no longer true. So here's an example. I think you can, if you're not familiar with Nostra flows, you can maybe follow this example. If you take the 2 torus and you'd find, let's say, maybe F, then this is the automorphism given by, let's say, 2, 1, 1, 1. So, I mean, 2, 1, 1, 1, that matrix acting on R2, and then it descends to an automorphism of the torus. And then you make a manifold M, which is going to be the 2 torus cross unit interval, but then with an identification. And the identification is going to be that, say, point x1 is going to be identified with f of x 0. And that's a perfectly good compact free manifold. And then you can define a flow by I sub t of, let's say, xs. Well, you just add t in the second coordinate, but do it mod the identification. And that's an example of a transitive Nostra flow. And then there's obviously the natural Z cover. Where you just sort of unwrap things. But if you think about the lifted flow there, that has no periodic orbits. So the flow is just going from left to right. So even though Z's amenable, you get no periodic orbit growth in the cover. So is there anything you can say? Well, yes, there is, fortunately, otherwise this talk would come to a screeching halt. It turns out that the correct comparison is not to compare what happens in the cover with what happens in the base. It's to compare with something else. So what you want to do, I suppose you've got your flow on the base, and you've got some arbitrary cover with the lifted flow, and here the covering group is G. What you want to do in between is look at the maximal abelian subcover. So M bar is the maximal abelian subcover of M tilde. So the group here is the abelianization like that. And so you can also define an H for this. So here let's call the flow phi bar. And so there's a theorem, Dougall, myself, appeared in 21, that you have H for phi tilde is equal to H for phi bar if and only if G is amenable. Okay. So the amenability dichotomy is restored provided you compare with the right thing. And from a ergodic theory point of view, another nice thing about this result, which I won't go into in detail, is that this quantity for abelian covers is actually well understood. It's given as the supremum of measure theoretic entropies for the base flow that satisfies some constraints. And in fact, there's a unique measure that realizes that supremum, and it's an equilibrium state. So the ergodic theory of that is well understood. So this is kind of a nice thing you're comparing with. It's not just some other random number. Okay, so we've got over 10 minutes left. And now I want to go back to random walks. Because the same kind of ideas can be used to think about the Kesten type result for random walks that no longer have to be symmetric. I should say that there's a kind of grand sort of analogy going here. So if you've got a symmetric random walk, we're somehow comparing that to a geodesic flow, and a geodesic flow is symmetric in the sense that there's a time reversal symmetry. If you take a unit tangent vector and send it to minus that, then that map conjugates flowing for time t with flowing for time minus t. So maybe it's kind of natural then to think for general transfer flows back to random walks without the symmetry. So let's go back to random walks. So G as before. So G is countable, but now we're going to assume that it's finitely generated as well. And mu is non-degenerate, but not necessarily symmetric. And then we're going to think about abelianizing the group. So G modus commutator, the abelianization, is going to be isomorphic to ZK cross, or, well, if it's additively plus, finite, some finite torsion group, for some k greater or equal to 0. So if k is 0, then the situation is essentially trivial, and what happens is the same as in the symmetric case. So let's suppose that k is at least 1. And so we want to work out what happens when we push forward to here. We can just mod out the torsion. And so let's just think about a map pi going from G to, I'll just write ZK, but it's the natural projection homomorphism. And then I want to talk about a measure which is the push forward of this mu bar is the push forward of mu. Okay, and so it turns out that now the right comparison in the non-symmetric case is between the spectral radius for the original walk and for the walk on the abelianization.
I mean, are you assuming finite support or something?
No.
Maybe push it forward, but
I mean, well, so yeah, I mean the mu bar of some element m is the sum of the measures of everything that projects to there.
yeah,
But that can't be more than one because it's a probability measure up above.
Oh, yeah, absolutely.
Okay, so well, imminent. There's no. I mean, it will go on the archive sometime this year, hopefully very soon. So I won't write anything. But okay, so the statement is that the spectral radii. Let's see. Bar are equal if and only if G is amenable. Okay. And no, the only condition for this is non-degeneracy. There's no moment condition. Okay, so I want to, well, firstly, let me characterize this quantity. So this is now classical stuff of Stone, Charles Stone, from the 1960s. So if you think about this function, var phi, so this will be defined on Rk to R plus union plus infinity, and it's defined by I bar of V is, well, you can define it in terms of mu, or in terms of mu bar. So this is a convex function, and Stone showed that it has a unique finite minimum, and that's exactly what gives you this. So there exists a unique, let's call it psi, in Rk, such that psi equals minimum phi. And then That's what gives you the spectral radius here. And now in the last few minutes, actually I probably went a little bit too fast. I've now got, I think, 5 or 6 minutes for this. I want to talk about what was going to be in Rhiannon's talk, which is going to be about ratio limit theorems. Okay, so, I mean, in an ideal world, you'd like to study this convolution for any element and understand its asymptotics. Okay, so that would be called the local limit theorem. And there are some particular situations where it's understood, obviously for integer lattices, and then for hyperbolic groups by Lally and Gazelle. But in general, it's probably too hard at the moment. So the next best thing might be to understand ratios. So maybe you might look at what happens for an element G and say divide by what happens for the identity and ask, what's the limit? Okay, so there's an obvious problem with this. You have to, a technical issue, that if for a lot of random walks, this will be 0 on, say, for odd n, something like that. But you just assume your walk is aperiodic, which gets around that. So we, let's just follow that. Okay, so we'll say that mu is aperiodic if there exists some n0 such that mu star n of the identity is positive for all n greater or equal to n0. And let's suppose we have that. Now that there was an old result of Ave for, so I'm going to talk about amenable groups now. And this is related to the character being able to work with the characterization here. There's an old theorem of Ave that people that went to Adam's talk yesterday have seen. 1973, that if G is amenable and mu is symmetric, so we're back with the symmetric condition again, symmetric and aperiodic. Then the limit as n goes to infinity, start n of G over of E is equal to 1 for all G in G. But now we're going to have a result which doesn't require the measure to be symmetric. And again, it will be in the same paper as this. So I'm just now assuming G amenable and mu is aperiodic. And so now we're going to have the same limit. Now, it's not only will this limit exist, we can say exactly what it is. So it's e to the minus inner product of, it didn't break, psi with pi of g, where the psi is the psi that Stone gives us from there. Again, it's all in G. So I think that's where I should stop. Thank you.